Hi everybody. Today I'm going to be covering graphical analysis of vectors. This is for Chapter 3, Sections 1 through 3 in the course textbook that we're using for Physics 1103, which is Gian Coley's Physics Principles and Applications. I also use some really nice resources in this lecture from Surway and Jewett's Physics for Scientists and Engineers. This is also a really great book, but it's usually used for the calculus-based section. However, since we're dealing with graphical addition, it doesn't really matter yet. Okay, so first a reminder. We covered this in an earlier lecture, but remember what the difference is between a vector and a scalar. A scalar quantity is completely specified by a single value, and it has units but no direction. So if I go for a run, for example, I might say, I ran 3 miles today, and that's a scalar, because I don't give you what direction I ran. A vector quantity, however, has a magnitude and a direction. So I might say, to get to school, I have to run 3 miles due east. That's a vector because I'm telling you that in order to get from my house to the university, I have to run 3 miles due east of my current position. Okay? So it's got a magnitude, 3 miles, and it's got a direction, east. So when we represent vectors graphically, we use arrows. So for example here, we've got an arrow indicating that a person started at point A and then their final destination ended them at point B. We call the origin of the vector the tail of the vector there at point A, and we call the destination there the tip of the vector where we ended up at point B. Okay? Now, there's a difference in distance and displacement. This was also something that we covered in an earlier lecture. The distance is the scalar quantity. So, for example, let's say that my initial position was point A and my final position was point B, but I took a really roundabout path to get there. Well, instead of just 3 miles, I might have ended up running 5 miles total, but because I did that crazy dashed path and did a loop, right, I ran 5 miles, but the direct line between A and B was only 3 miles. And here that might be northeast, okay? So that's the difference between displacement and distance, okay? The distance is the scalar, the total distance ran, and the displacement is the final minus the initial position and is indicated by this vector here in black, okay? Now, earlier in chapters, we just dealt with one-dimensional motion. But now we're going to allow our objects to move in 2 dimensions. We're still going to use the vector notation where we use bold type and or an arrow above the thing, above the letter, to indicate a vector. If it's a magnitude of the vector, just the length of the vector, for example, which is a scalar quantity, we'll use no bold type and no arrow to indicate that. Okay? When you're handwriting it, since you can't do bold type on your homework, make sure you put an arrow above it to indicate a vector. Now, 2 vectors are equal if they have the same magnitude and the same direction. In other words, 3 miles due east would be the same vector in New York, Chicago, or San Francisco. You're still running 3 miles and you're still running due east. So if you're looking at a 2-dimensional coordinate system, for example, all these red vectors are the same because they have the same length and they all point in the same direction. And you can slide them around however you want as long as you don't change their direction or length. Alright, so these are all equal vectors here. This concept is going to be very important when I introduce the graphical addition of vectors in just a few minutes. Now, when you add vectors, you can't just add their lengths and call it a day because they have a direction. For example, if I added the vector 3 miles east to the vector 3 miles west, I'd get nothing. They'd cancel each other out. Whereas if I just added the magnitudes, I would get 3 plus 3 is 6 miles. And that's definitely not right, okay? So, another thing to take into account is that the units have to be the same. You can't add a displacement to a velocity, for example. That doesn't even make sense. 3 miles plus 3 miles per hour is nothing. You can't add things with dissimilar units. Now, today we're going to cover the graphical method, which is sometimes called the tip-to-tail method of vector addition, in which you use scale drawings to add the vectors. In a later lecture in class, we're going to cover algebraic methods, for adding vectors, which is more convenient lots of times, but sometimes a little bit more mathematically complicated. So when you're adding vectors graphically, you have to be sure to choose a length scale. For example, if you choose that length right there to be 1 meter, then that always better be 1 meter. Otherwise you're going to end up with weird answers when you try to add your vectors. So pick a scale and stick with it. What you're going to do to add vectors is you're going to draw your first vector. Let's call it A. And we're going to give it the appropriate length and in the specified direction with respect to the coordinate system that you've laid out. Then you're going to draw the next vector with its appropriate length and its direction with respect to the coordinate system, and you're going to put it at the end of vector A, okay? And you're going to add it in. This is a lot easier to show in a picture. So here's the image. Let's say that we want to add these two vectors, A and B. This is why it's called the tip-to-tail method, because I take vector A, that's my first vector, and then I put vector B right at the end there of vector A and then draw it, okay? Now, my resultant vector, which I call here R, is going to start at the beginning of vector A and going to end at the end of vector B. So my resultant vector, R is equal to A plus B, is that much longer vector up and to the right that you see in the diagram, okay? So that's the tip-to-tail method of vector addition. If you have a lot of vectors, you just keep adding on. So for example, if I had vectors A, B, C, and D indicated here, and I wanted to add all of them, then I would just start with vector A, and then put the beginning of vector B at the end of vector A and draw it, and then put the beginning of vector C at the end of vector B and draw it, and then same thing for D, right? And then once I've done that for all my vectors, I connect the beginning of the first vector to the end of the last vector, and that gives me my resultant. In this case, R here. So when you add two vectors, honestly, it doesn't really matter what order you add them in. This is called the commutative law of addition. This is very similar to adding scalars, for example. 3 plus 4 is 7, but so is 4 plus 3. It's 7. It doesn't matter whether you start with the 3 first or the 4 first. Same thing here for vectors. To show this, I've shown you what vector A plus B looks like, and then I've shown you the same thing for vector B plus A. You can see that you get the same vector, okay? So here on the bottom is A plus B. So A starts first, and then I put the beginning of vector B at the end of vector A, and then I draw it. And then I connect my resultant vector, called here R, from the beginning of A to the end of B. But you can see that the same thing happens if I start with B and then add A on second. I get the same vector. So this is the commutative law of addition. Doesn't matter what order you add them. If you're adding more than two vectors, it also doesn't matter how you group them, okay? So I could add A and then add plus B plus C, or I could do A plus B first and then add C. It really doesn't matter. So I can switch the order of the addition however I like, and it will still be the same resultant vector. I hope that's clear. Remember, it's very important. When you add vectors, all those vectors have to have the same units. They all, in other words, have to be the same type of quantity. It makes no sense to add a velocity and an acceleration. It just doesn't make sense. Now, we're going to say that the negative of a vector is defined as the vector that is the same length but points in the completely opposite direction. If you add A plus negative A, you want 0, right? Just like 3 plus negative 3 is 0 for scalars, you want the same thing to be true for vectors. So let's say that this is A and this is negative A. Then when I add those two things together, I should end up back where I started. So my net displacement there would be 0, okay? So it has the same magnitude, but it points in the opposite direction. Okay, let's do an example for a vector addition problem. Let's say that we have these three vectors indicated here, A1, A2, and A3. So which one of these choices shows you A1 plus A2 plus A3? Now in this drawing, vectors 1 and 2 are the same length, and vector 3 is twice the length of vectors 1 and 2. And they're all tilted at 45 degrees from the horizontal and the vertical, okay? So I'm going to work this here using graphical addition on the next slide, all right? So here's vector A1, right? I start off there. Then I add vector A2 using the tip to tail method, starting the beginning of vector A2 at the end of vector A1 and draw it. And now I've got to add in vector A3. So I'm going to put the beginning of vector A3 at the end of vector A2 and then draw it. Now I connect the beginning of vector A1 to the end of vector A3, and that's my resultant vector. Now you can see that when that happens, I get a vector that points straight down, right? So that is answer C right here on my multiple choice question. Here's another question. If two vectors are given such that a plus b equals 0, what can you say about the magnitude and direction of vectors a and b? Is it A, same magnitude but any direction, B, same magnitude but same direction, C, different magnitudes but must be in the same direction, D, same magnitude but must be in opposite directions, or E, different magnitudes but must be in opposite directions? Okay, well, let's take these answers one at a time. Here's my two vectors, okay? If I added A and B, right? A, could I choose any old direction for B and get 0? No, right? If I connect my knuckle to the tip of my fingernail right there, then I'm only going to get 0 if I do that, okay? And then my knuckle and the tip of my second finger there are in the same place, and that means my net displacement would be 0. So which answer is that? Well, that's answer D. Same magnitude, but must be in opposite directions. Another way to think of it is to solve it algebraically. If a plus b equals 0, then b equals minus a, which is the same magnitude as a, but opposite in direction, as we just defined. So, answer B. So here, I have A in the blue and B in the red, and they add to a net displacement of 0. Now, subtracting vectors is a special case of vector addition. So, if you're doing A minus B, then you can do A plus negative B, okay? It's important to realize that subtracting vectors isn't the same as adding them. In other words, there's no commutative property of subtraction. Even in scalars, 4 minus 3 doesn't equal 3 minus 4. Same thing for vectors. So when you're subtracting vectors, it's important to keep the order the same. Okay, so here I show a tip-to-tail method for adding these things. In this case, I call the resultant vector C, which is A plus minus B. If A is shown here and B is the dashed vector shown right here, then the opposite of B would have the same length but point 180 degrees in the opposite direction. And that's that minus B vector indicated in the solid orange line. Then I connect the beginning of vector A to the end of vector minus B, and there you have it. It's C, which is A minus B. So that's the tip-to-tail method for subtracting vectors. Basically, you just flip the direction of the second vector that you're subtracting off, and then add that. Finally, let's talk about what happens if you multiply or divide a vector by a scalar. Basically, what you're doing is you're changing the length. And if it's a negative scalar, you're also flipping the direction. Remember that if we had vector A and we multiplied it times minus 1, then it pointed 180 degrees in the opposite direction. So if you multiply a vector times the negative of it, the negative number, then it's going to flip the direction. However, let's say that I have some constant C, which is positive, right, and greater than 1. That's shown here. If I multiply A times C, then what I'm doing is I'm keeping the direction the same, but I'm changing the length. In other words, let's say here that C was 2. Well, this vector here is twice as long as the first vector, A, okay? So I've changed the length, but I've kept the direction the same. If I multiply it by a scalar which is less than 1, then I shrink it. So if I had a vector A and then multiplied it times a scalar of 1/2, then I would have a new vector which was the same direction as the original vector but half the length. So that's how you multiply and divide by a scalar. Okay, I hope all that is pretty clear. If you have any questions, please do let me know, and I'll see you in class.